Our keynote speaker, Spencer Wells, is a geneticist, an anthropologist, an author, and an entrepreneur. For over a decade, he was an explorer in residence of the National Geographic Society and director of the Genographic Project, which has collected and analyzed DNA samples from hundreds of thousands of people around the world to decipher just how our ancestors populated the planet. And in the process, they launched the consumer genomics industry. Dr. Wells graduated Phi Beta Kappa from the University of Texas at Austin. He received his PhD from Harvard University and conducted postdoctoral work at both Stanford and Oxford. He has appeared in numerous documentary films and is the author of 3 books: The Journey of Man, Deep Ancestry, and Pandora's Seed. His fieldwork has taken him to more than 100 countries around the world, where Dr. Wells has worked with everyone from the heads of government to Fortune 500 executives to tribal chieftains. He lives in Austin, Texas, and is the Chief Product Officer of Embark Veterinary, a startup consumer genomics company focused on pet wellness. Dr. Wells is an adjunct professor also at the University of Texas and even owner of a blues club in Austin. We're very excited about hearing what Dr. Wells has to say. Please join me in welcoming Dr. Spencer Wells. Welcome, sir.
Thank you. All right, good morning. Greetings from Austin, Texas, where we love our brisket. It's great to be here. I'd like to thank the Angus Association for inviting me to come and talk, and to tell you a little bit about the science behind what has become the consumer genomics industry, which we launched over a decade ago. It's a long story, and it's going to take us through about 200,000 years of human history. Now, as you heard, I am a human population geneticist by training. And what do we do as human population geneticists? Well, really our goal, the overarching theme in our work, is to try and explain the patterns of human diversity we see around the world. We travel, we walk down the street in a major city, we see people who seem to be so different from ourselves and from each other. How did those differences arise? And how did we scatter to every corner of the earth? I mean, put yourself back in the time of the European age of exploration. You're crashing around the Pacific with Captain Cook, and every time you come ashore, there are people living there. How did they get there? And how are they related to other people you might have met before? That's really the overarching theme of our work. But like any big theme in science, we can break it down into sub-themes or questions that we can start to chip away at, using the tools of science, gathering data, formulating hypotheses, coming down on one side or the other. The first question we can ask is one of origins. Are we in fact all related to each other? And if so, how closely? And the second is one of journey. Well, if we are all related, if we do spring from a common source as a species, how do we come to populate every corner of the globe? In the process, generating these patterns that we see today. Well, historically, this has been studied through paleoanthropology and archaeology. Paleoanthropology, going out and digging up bones out of the ground, like the Leakey family, famously, in Africa, and based largely on morphology, often skull shape. This looks a little bit more like my cousin Fred than that does. You can infer all sorts of things, but what I'd like to suggest, though, is that the field of paleoanthropology gives us lots of fascinating possibilities about our past and where we came from, but not the probabilities about direct lines of descent that we really want. Possibilities, but not probabilities. What do I mean by that? Well, this is a great example. What you're looking at here are 3 potential human ancestors. From left to right, Homo erectus, Homo habilis, and Paranthropus boisei, a robust Australopithecine, all uncovered from the same location in northern Kenya, and all dating from roughly the same time, about 2 million years ago. So we've got 3 potential ancestors living in the same place at the same time. Which one of these guys am I actually directly related to, descended from? I don't know. Possibilities about our story and our past, but not the probabilities about direct lines of descent again. Well, we as population geneticists take a slightly different approach. Instead of going out and digging things up out of the ground and guessing at how they may connect up to the present, we start in the present and we work our way back in time. The question of origin is actually a genealogical question. We take a genealogical approach. We all know that we had parents, those parents had parents, and so on. Genealogy, the second most popular hobby in the United States, after gardening, I'm told. Apparently it's poised to overtake it. I'm sure many of you in the audience have built family trees. Most people can go back a few generations, some as much as 1,000 years or so, but at some point, everybody's family tree hits what the genealogists call a brick wall, a point where there is no written record, those records run out, and we simply enter this dark and mysterious realm we call history, and ultimately prehistory. But it turns out we're all carrying what is, in effect, a historical document inside of ourselves, inside of nearly every cell in our body, in our DNA. And that allows us to see back beyond that brick wall, beyond the written record, back to our very earliest days on planet Earth. Now, a quick primer on DNA for those of you who have not taken molecular genetics recently. There will be a quiz at the end. Long linear molecule, the famous double helix described by Watson and Crick back in 1953, for which they later won the Nobel Prize. It's composed of 4 subunits. We denote them A, C, G, and T. And it's the sequence of these A's, C's, G's, and T's, billions of them, in fact, that basically make the blueprint to create another version of you. This is a lot of information, billions of these A's, C's, G's, and T's. How much? Well, if you took all of the DNA, 1 genome's worth, out of 1 tiny microscopic cell in your body, and you stretched it end to end, it would be about 6 feet long. Pretty crazy. And that's packed into a cell you can't even see. So it's very, very, very thin. If you took all of the DNA out of every cell in your body, or trillions of cells, it would reach from here to the sun and back hundreds of times. So it's a lot of information. And in every generation, you have to copy this information to pass it on. It's like copying the longest book you can imagine. Think of, say, War and Peace, but imagine 1,000 volumes of that. And you've got to copy this in roughly 8 hours, which is how long it takes your cells to do this. So what are you going to do? Well, this is really important information. So you're going to sit down with your cup of coffee and you're going to pay attention and you're going to check and double check. You're going to proofread to make sure you don't make mistakes. Because again, it's important. You're creating the next generation. But inevitably, what is going to happen as you're doing this copying process? You're going to make a typo, spelling mistake. Change an I to an E, or in the case of DNA, a C to a G. These spelling mistakes or typos at the genetic level are known as mutations. And when they occur and they get passed down through the generations, they become markers of descent, such that if you share one of these changes in your DNA with another person, it means you share an ancestor at some point in the past, the person who first had that change in their DNA and passed it on to the two of you. And these changes occur at a relatively regular rate, ticking off like a clock in every generation, 100 mutations per genome, which is a very low rate if you think about the billions of nucleotides that we have. 100 per genome per generation, ticking off like a clock. So it gives us a way to measure the timing of these events that we're interested in studying. Now, what do these genetic markers, these typos, look like? Well, what you're looking at here are 5 DNA sequences, 5 different individuals, in this case 5 men, who've had the same region of one of their chromosomes, the Y chromosome, which is the chromosome that makes men men. They've had the same region sequenced, and they've been lined up. And the first thing you'll notice if you compare those sequences, reading down through them, is that they're basically identical. That's the first thing that comes out of every one of our studies of human genetic variation. Humans are 99.9% identical at the DNA level. We only differ on average at 1 in every 1,000 nucleotides. This is from someone we're not even closely related to. It's a remarkably low level of genetic variation. So it's actually quite difficult to find these genetic markers that we use to get at the questions of origins and journey. But if you look down, about 3/4 of the way down, you'll see a run of Gs on the lower 4 sequences, G, 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 G. On the top sequence, however, you see G, A, G. That single letter change from a G to an A, that's a genetic marker. If you share that A with another person, you share an ancestor, the person who first had that change in their DNA and passed it on to the two of you. Now, by looking at the pattern of these genetic markers and people from all over the world and asking a really open-ended question, how do they start to coalesce into ever deeper branches of the tree? We can, in effect, build a genetic tree for everybody alive today, based on the shared markers that we can find in their DNA. We focused in particular, for this purpose, on 2 pieces of DNA that have proven to be really important to our studies of human journeys. Mitochondrial DNA, mtDNA on the left, which traces a purely maternal line of descent. Everybody has it, but only mothers pass it on. So it tells you about your mother's 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 mother. The Y chromosome on the right, which is kind of the male equivalent. It's, again, the piece of DNA that makes men men. And it's passed down through a purely paternal line, so it tells you about your father's 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 father. By looking at the pattern of markers on these pieces of DNA in the human genome, people from around the world, we built what are in effect family trees for everybody alive today. Everybody sitting in this room, in fact, all 7.6 billion people walking around on planet Earth today, fall somewhere onto one of the branches of these trees. Pretty amazing. Now, these are actually very simplified versions of the trees. There are actually thousands of branches that we've discovered over the last couple of decades. But sitting out there, if you're not used to looking at trees, they still look kind of complicated. So what's the take-home message here? Well, let's simplify them even more, combine them, turn them on their side so that the root is at the bottom, the branches are coming off the top, like a real tree. What's the take-home message here? Well, it's that the longest branches on the tree are found in African populations. And because the length of the branches is proportional to the number of these changes that have been occurring over time, that clock ticking off mutationally every generation, what that tells us is that Africans have been accumulating genetic diversity for longer than any other group. And therefore, that our species originated in Africa. Mitochondrial Eve, Y chromosome Adam, living in Africa around 200,000 years ago. And it's only within the last 60,000 years that our species has started to leave that continent to populate the rest of the world. It's only 2,000 human generations. It's the blink of an eye, if you will, if you think about the history of the Earth. Moving along a southern route, making it to Australia, via southern Asia by around 50,000 years ago, a later inland route via the Middle East into Central Asia, populating Europe by 35,000 years ago, and moving into the Americas across the Bering land bridge that existed during the last ice age between 15 and 20,000 years ago. An amazing story, the great Paleolithic wanderings of our species. And really getting at the details of these journeys that we've all followed is the subject of my life's work, and was the subject of the Genographic Project, which, as you heard, I directed at the National Geographic Society from 2005 to 2015. Now, the Genographic Project had 3 core components. At its heart, it was a research effort, field research done by myself. Believe me, I've traveled a lot, I've got a lot of frequent flyer miles, and a team of people, colleagues around the world, focusing on indigenous and traditional peoples, living in far-flung places, northern Chad, Tajikistan, Papua New Guinea. Now, why are indigenous and traditional peoples so important? Well, think about your own genetic story, your DNA, in the context of where you are now. I'll think about mine out loud. I have ancestors from all over northern and western Europe. I live in central Texas now. What does my DNA tell you about the ancient history of those places? Not a lot, because my ancestors have moved around a lot in the last few hundred years. Ideally, to get at these deeper stories, how we populated the world, we need to be looking at people who've lived in the same place for hundreds, thousands, even tens of thousands of years in some cases. Those are the world's indigenous and traditional peoples. So that was the core of the scientific research. But when we were designing the project, way back in 2003, 2004, I felt very strongly that this should be the story of everybody. Everybody should be able to participate in principle. It's not just the story of the world's 100 or 200 million indigenous people. It's the story of all 7+ billion of us. So we created what we call the public participation component. We built a DNA testing kit, which nobody was really doing at the time. Seemed a little crazy, but I had glimmers of ideas that this might be interesting to some people. We had done some preliminary testing around a film that I made that came out on PBS in 2003 called The Journey of Man, and there was a lot of interest on the part of the people we approached in getting their side of the story. So we created an opportunity for people to find out something about their history, their genetic history, and become a part of the research, this public participation component. Moreover, by buying one of these kits, you help to support the research we were doing around the world, the basic scientific research with the indigenous people, as well as the third component, the Legacy Fund. And this was a grant-giving entity within the project, driven entirely by the sales of the kit. It was all nonprofit. National Geographic is a 501c3. The Legacy Fund, a way to give something tangible back to the world's indigenous and traditional people, many of whom are the poorest of the poor in already very poor places. They're forced to leave behind their ancient villages, their homelands, typically moving to a growing megacity. Think of Sao Paulo or Bombay. When they do, they become part of the melting pot. Their kids stop speaking the old language, they stop hearing the stories. Within a generation or two, that culture has effectively gone extinct. Linguists tell us of the 6,000+ languages spoken around the world today, by the end of this century, between half and 90% will be gone forever, extinct. We're losing a language every 2 weeks. And this parallels the biodiversity crisis that biologists talk about so often. So the Legacy Fund, a way to give something back to those people, trying to preserve their culture, their connection to the old ways, the stories, the languages, and so on. Cultural diversity, a very important part of what it means to be human. Well, as I said, I directed the project. IBM is our partner from 2005 to 2015. How did we do? Well, like any big scientific effort, it's still ongoing. There's still research that's being done on the samples that we collected. There's still papers being published. So far, we collected around 72,000 samples from indigenous and traditional groups on every inhabited continent, representing over 1,000 different populations. More than 60 scientific publications have resulted so far. So very much a success on the scientific side. We built capacity in South America, India, parts of East Asia, and so on, which didn't have access, at the time we started at least, to some of the advanced genetic technologies that we were using. So we feel that scientifically we really created something of value that is going on. It's continuing to yield interesting results. Now, the big surprise for us was the public participation side and how successful that became. I stepped out on stage on April 13th, 2005, to announce the Genographic Project to the world. Huge effort, tens of millions of dollars worth of investment, big partners like IBM and the Waite Family Foundation. We had ambassadors in the room in Washington, D.C., CNN interviews, waiting as soon as I came off the stage. Right before I stepped out on stage, though, the then CEO of National Geographic, a guy named John Fahey, who had previously been head of Time Life, pulled me aside and he said, "Spencer, listen, we love this project. It's one of the biggest things we've ever done in National Geographic's history, going back over a century. We're really excited about this and all the science that's going to come out, the stories that are going to result. But this whole consumer DNA testing thing, public participation, just kind of soft pedal that, because nobody's going to spend $100 to test their DNA. If you sell 1,000 of these in the next few years, You'll be lucky. And I said, okay, John, yeah, I'll take that bet. I think we're going to sell well over 1,000. So stepped out, made the announcement, and by the end of that day, the day we launched, we'd sold 10,000 consumer genetics kits. Something that didn't really exist at that time. It launched an industry. We hit 100,000 by the end of 2005. And suddenly we were off and running. And I'll talk about the additional companies that came online, 23andMe in 2007 and so on after that. As of today, we've sold over 900,000 kits through Genographic to people living in over 140 different countries, all over the world. Kazakhstan, French Guiana, Vatican City, sold 2 there. I would really love to know who bought them and what the results were. And obviously, again, in addition to launching the industry, it generated a fair amount of money for the research that we were doing out in the field, as well as the legacy grants. And we were able to give away over $2.5 million over the decade-long project. Grants, over 95 grants to people around the world. Now, I'm often asked, as I'm thinking about, what we did in this project, what's the big surprise for you? Any scientific surprises? Of course there were. We discovered a lot of cool new things. Population structure in Afghanistan, coevolution of languages and geography in the Caucasus, all sorts of details that I'm not going to go into here. But the biggest surprise for me was how excited people were about digging into their results, understanding more about their genetic heritage and where they came from. And the power of what we started to call citizen science, enabling people who don't have a fancy PhD to get involved in analyzing their own data, providing them with the tools and the knowledge they need to really dig deeper and understand more about where they came from. Now, great example of this, a woman wrote into the project back in, I believe it was 2008, 2009, and she said, listen, love what you're doing. Lots of members of my extended family have tested themselves. Whenever we get together for Thanksgiving or other family holidays, we all compare our DNA results and talk about how we could be connected to each other and all this. But unfortunately, in my case, you seem to have gotten the actual results wrong. I'd like you to retest me because you told me that I am carrying a Central Asian or a Siberian mitochondrial DNA lineage. And I know for a fact that my ancestors came from a little village just outside of Budapest in Hungary, which is what you're looking at here. I can show you church records, she said, going back to the 16th century. So clearly, I've got to be Hungarian, Central European, not Asian. Thank you very much, et cetera, et cetera. Well, when I got this email, I was really excited, not because I enjoy asking the lab to cherry pick one sample out of hundreds of thousands. They tend to get kind of annoyed about that. But rather, because the Hungarians are a really interesting group. Now, most of the languages in Europe, the one I'm speaking now, for instance, English, German, French, Spanish, Italian, all fall into what is known as the Indo-European language family. Languages that descend from a common ancestor that existed between 6,000 and 8,000 years ago, probably somewhere in Eastern Europe. It includes languages spoken down in Iran today. Farsi is part of the Indo-European language family, as well as Hindi, spoken in India. So it's this broad kind of Western, Southern Eurasian set of languages that, again, includes pretty much all the languages in Europe, except for a couple of outliers. There's Basque, which is spoken in northeastern Spain and southwestern France, unrelated to any other language, what we call a linguistic isolate. Could have come here from Mars, for all we know, at least according to the linguists. Maybe some distant relationships to languages spoken in the Middle East and the Caucasus Mountains, but effectively off on its own. So there's Basque, not Indo-European, and then there's Hungarian, which is another outlier, but it's actually part of another language family. So it's related to Finnish and the language spoken by the Sami people, the Laplanders, the reindeer herders living in northern Scandinavia. So forming a branch, the Finno-Ugric branch, of what's more broadly called the Uralic language family. And as the name Uralic suggest, the center of diversity is around the Ural Mountains and places further east. It's an Asian language family. Now, this makes sense because we know that the ancestors of the Hungarians arrived in Central Europe around 1,000 years ago, bringing with them their culture. They settled there, and they completely replaced the language that was spoken there before, which must have been related to Polish or Czech or Slovak or some of the surrounding languages. Now, when geneticists see an example of language replacement like this, we get really excited. And we say, well, we should go out and test these people, see if there's a genetic signal. And so we collect 50 or 100 DNA samples from the Hungarian population, what we typically do in these studies. And lo and behold, the Hungarians look genetically like their neighbors who don't speak Hungarian. So there was a huge cultural impact with a language replacement, but we don't see any genetic evidence for it. Now, when this woman wrote into the project, the reason I got really excited is I said, well, listen, this is an opportunity to utilize that consumer database. Maybe there are a lot of Hungarians in there. How many do we have? Well, it turned out at that time we had over 2,300 people with known Hungarian ancestry. By far and away the largest sample of Hungarians that had ever been put together before. And when we looked at their genetic lineages, around 2 to 3% were Asian in origin. So the power of large amounts of data, we were expecting this as we collected hundreds of thousands of samples. We should start to see things that we didn't see with fewer DNA samples. But the really exciting part of this story, and the reason why I'm using it as an example, is because we wouldn't have necessarily thought to go in and look for this pattern if this woman hadn't flagged her unusual result. So that's the power of citizen science. Instead of a few scientists with PhDs deciding what they want to focus on for their research, you allow everybody, driven by curiosity, to find out their own information. Utilizing the tools that you create, so there has to be some scientific validity, but open up the database, for instance. Allow people to start to go in and explore these patterns, driven by their own curiosity. Decentralize the science, bring it back to the people, if you will. So, very exciting. Now, I want to talk briefly about two revolutions that have happened in our field, genetics more broadly, but in particular in human population genetics, that have happened in the last really 6-7 years or so. The first is the drop in price and the increase in speed of sequencing entire genomes. Now, I'm going to date myself here. I started my PhD back in 1989. At that time, we were still debating whether it was theoretically possible to sequence an entire human genome using the methods that we had at the time, and then you multiply across all the people who were students and postdocs and technicians in the labs doing this stuff. It would theoretically take centuries to sequence just one human genome, all those billions of nucleotides. That's completely changed in the last few years, and I'll talk about that more in a minute. The other revolution that's happened is a revolution in our ability to get DNA out of ancient material. So for most genetic studies, we're using people, or if you're studying cattle genetics, cattle that are alive today. It turns out, though, that sometimes DNA sticks around after death, in some cases for tens of thousands of years. And you can actually extract DNA from ancient remains that have been carbon dated, all about the culture that's associated with them, and they can provide amazing insights into what was going on at specific points in the past, like a time machine. Well, the revolution in DNA sequencing really started around 2007. So again, thinking back to when I started my PhD in 1989, it took over a decade for the Human Genome Project, which I'm sure most of you have heard of, to complete that first DNA sequence. Over a decade, and it cost billions of dollars to do that. Now, as we start to move forward into the post-genomic era, as we start to look at additional genomes, the price starts to drop, but it's still following something known as Moore's Law. Gordon Moore, back in the early 70s, calculated that the number of microprocessors you can fit into a computer chip is going to roughly double every couple of years. And that has held true for decades now. So he was a pretty smart guy. DNA sequencing was following roughly Moore's law for several years after the completion of that first human genome. And then in 2007, something happened. The launch of what is known as next generation sequencing technology. Basically miniaturizing everything, high resolution optics, so I won't go into the details, but it allowed us to take a quantum leap forward in sequencing DNA, and the cost of sequencing a genome fell off a cliff. This is the most rapidly changing technology in human history. It's virtually impossible to predict what technology you might be using in 5 years today. What it's served to do, though, is to make genome sequencing very, very easy and very quick. It's now possible to sequence a human genome for less than $1,000 in less than a day. Again, it took billions of dollars and over a decade to get that first one. So it's really incredible, and it's providing us as scientists with a huge amount of data. Data to finally answer a lot of questions, including in human population genetics. Now, the human genome isn't just one continuous piece of DNA. It's arrayed into chromosomes. There are 23 pairs of them, thus the name 23andMe, one of the major consumer genomics companies. And these pairs, in every generation, undergo a shuffling process. They actually exchange information along their entire length. It's a process known as recombination. Now, for a lot of our work, this makes estimating the timing of some of the events that have occurred, these migration patterns and so on, very, very difficult. But it turns out that recombination itself can be an awesome tool for understanding a lot of the details of how the genome has changed over time. The genome has not simply been a passenger as we've moved around the world, with mutations ticking off, allowing us to study these migratory routes. It's also actively adapted and changed. Now, if we imagine many generations of that shuffling process going on, we ultimately end up with kind of a random background pattern of genetic variation we expect to see in human populations. And because we have this kind of random expectation, it allows us to go in and look for instances where we don't see that background pattern, where we see a deviation, a statistically significant deviation. I like to think of it, as the father of 2 daughters, as imagine you have a multicolored beaded necklace, and these are segments in your chromosomes, and you expect a kind of random background pattern in the colors that you're using, but occasionally you'll come across a section that's too similar among all the necklaces. What you would infer from this is that the little girls in this case had decided that this was really attractive, pretty. They decided to incorporate it into their necklaces. It was a trend. And so it increased in frequency, and now everybody sees it, or nearly everybody sees it in their necklace. We can do the same thing, statistically speaking, with whole genome sequences, except that we're not talking about beads on a necklace. We're talking about segments in the genome. And what this means, when we see this particular pattern, where you have a single small segment that's been driven to very high frequency in a population, is that there's been strong selection for a genetic variant in that region. It tells a story of how we have adapted to the environment around us. And it's pretty amazing. We can literally scan down through the genome and see these patterns. The strongest signal we see, the one over on the left, the LCT peak that you see there, that's lactase persistence. That's the ability to digest the sugar in milk into adulthood. And this is very common in people of European ancestry. It originated within the last 5,000 or 6,000 years. And strong selection for the ability to drink milk and eat cheese and yogurt has driven that to very high frequency in those populations. But there are stories like that across the entire genome. So the SLC gene that you see in the middle has to do with skin color. So that's an adaptation to lighter skin in northern latitudes in Europe. We have lots of adaptation to pathogens. So pathogens, viruses, bacteria have been a big driving factor. Adaptations to diet, particularly as we change from being hunter-gatherers 10,000 years ago to being farmers, and the spread of farming out of the Fertile Crescent in the Middle East. Lots of amazing stories that we can glean from all of this whole genome data. Now, the ancient DNA stories are also fascinating. It turns out that Neanderthals are cousins who left Africa roughly 500,000 years ago, so long before we did, living out in Eurasia when we start to leave around 60,000 years ago. The story had always been, well, there are no Neanderthals alive today, so we must have driven them to extinction. Except, it turns out, by sequencing the genome of first a single Neanderthal and now several Neanderthals, that before we did that, we interbred with them, such that the average non-African today is about 2% Neanderthal. So look to your left, look to your right, look at yourself. You're a little bit Neanderthal. We've discovered completely new species, the Denisovans, discovered from a tooth and a pinky bone from a little girl in a cave in Siberia, the Denisova cave, another human species that we didn't even know about, distantly related to the Neanderthals. We only know about this individual from their genome. So really starting to add in the detail about the complexities of human migration patterns and the human story. Now, of course, some of us are a little bit more Neanderthal than others. Aussie, relatively high Neanderthal percentage. The ancient DNA work also allows us to get answers to questions about things that we think of as being in the realm of history, recorded history. So not just stuff that happened tens of thousands of years ago, but stuff that happened in the last few thousand years. It's revealing, for instance, that there was a significant population replacement during the Bronze Age in Europe. We see evidence of killing fields all over Europe around this time. This is 4,000 or 5,000 years ago. There was clearly a population replacement at the same time. We can see that genetically by looking at ancient DNA. There was a 90% population turnover in Britain around this time. The arrival of the Bronze Age Bell Beaker people who replaced the people who were there before. So pretty scary time to be alive, but fascinating to reveal all of these details. Now, let's talk a little bit about consumer genomics. So again, we launched this industry effectively in 2005. There were a couple of cottage companies out there that were mostly working with academic labs. But in effect, the Genographic Project was the launch of the consumer genomics industry. Let's think a little bit about the sales figures. So if we go back to 2005, when we start to see that significant uptick with the launch of Genographic, 100,000 in that first year. We see it start to climb in a linear way. 23andMe launches in 2007. And 23andMe, I spoke to the founders, including Ann Wojcicki, the night before they were about to announce to the public, and she said, listen, the reason why we're able to do this is because you guys proved that there was a market there. They were offering at that time not only ancestry testing, but really a big focus on medical testing as well. They've since had to back off because of FDA regulations. Some of that is now coming back online. But the important thing in terms of this curve is that their launch price was $1,000. And so that didn't have a significant impact on the market. It was when they started to drop their prices in 2009, down below $400, that we started to see a little bit of a tick up. And then the big shift comes at the end of 2012 into 2013. And that's when Ancestry launched its test. Now, it wasn't selling a lot in those days, it was gathering a database. But Ancestry.com, the genealogy company, has the best-selling DNA test in the world now. And those shifts happened, as I said, around the end of 2012 into 2013. Around that time, the millionth person bought a DNA testing kit. It took a little over a year for the second millionth person to buy a DNA testing kit. And it took less than a year for the third millionth person to buy a kit. So the curve shifted. It was an inflection point where things really started to explode. Now, why was it happening at that point? Well, this is still the case. DNA has become part of the national consciousness. If you think back to 2005 when we launched Genographic, DNA was kind of scary. It was Jurassic Park. It was like clone armies and things like that. People were a little concerned, like what are you going to do with the DNA? People are just comfortable talking about it now. It actually is part of marketing campaigns for companies that have nothing to do with the genomics industry. Dell, for instance, last year ran a big campaign that literally showed a double helix with various aspects of their corporate culture and different brands and so on, identified as though they were genes in a DNA sequence. But other companies talk about, innovation being in their DNA. This really wasn't happening back in 2005. So DNA is just something that people have become comfortable with. It's part of the national consciousness now. People are also much more comfortable sharing their most private information. Now, when we launched Genographic, we had a random code, randomly generated. We didn't know which code went into which kit, but that random code in the kit was the only way you could log in and get your results. There was no way to ever attach a person to their genetic results. And that was meant to protect people, because there were a lot of concerns about privacy back in those days. We seem to have given up a lot of those concerns in the era of Facebook and Twitter and Snapchat and all the other stuff that we use to share very private, personal moments in our lives. People started telling us, we want to be able to create an account tied to our email address. And we said, no, listen, this is meant to protect you. Well, I forgot my code. It would be great if we could create an account. People have no issues these days, or very few issues, with sharing some of their most private information. And so that's been a big shift. And finally, by the time we hit 1 million people testing, it was quite likely that someone in your social circle had tested their DNA. I mean, I'm sure there are a few people in this room who have tested through one of the big testing companies. And you end up talking about this, and these people become influencers, and they say, well, I found out this really cool information, you should try it. Well, that played a role in the launch of the consumer genomics industry. I like to think of it kind of like the film industry, which is a really unusual industry, because you spend all this time and money making your product, making the film, and you spend a fortune during the initial launch, and if you don't make your money back almost immediately, within the first couple of weekends, it goes directly to Netflix. You're done with that thing. It's the rare film, My Big Fat Greek Wedding was a good example, that starts off slow and is allowed to build based on word of mouth and reviews and so on. And so this is what I think started to happen in the consumer genomics industry really in 2013, and no signs of flattening out or asymptoting at the top. The big 4 companies today, 23andMe, Genographic, Ancestry, by far and away the biggest, and Family Tree DNA. Ancestry, just to give you a sense of how big this has gotten, Ancestry alone, over Cyber Weekend, so that's Black Friday, Cyber Monday after Thanksgiving, last year sold 1.5 million kits in 4 days. This is a big business. More than 20 million people have now tested with all of those companies through this summer, and our biggest season is always in the fall leading up to the holidays. Last Christmas, consumer DNA kits are one of the biggest selling categories on Amazon. So right up there with the Echo and all the other big consumer products. So this has suddenly become a huge business. What's the prediction for the future? Well, in the future, I think we're all going to be sequenced, probably at birth, possibly even before birth. This is going to be part of the data cloud that you carry around with you. In the same way that you carry a credit history, or if you're younger, a college transcript, as you start to move out in the world and make your way. It's going to help you make decisions. Because of our belief in this, I've been involved with a company called Helix out in the San Francisco Bay Area, which is a spinoff of Illumina, which is the dominant technology company in the genomics space. I was a scientific advisor to Helix when they launched, and now have a small consumer genomics company building apps for what they believe is going to become the ecosystem of the future, where everybody has their genome sequenced. That's of some utility today. We can tell you a lot about your ancestry, but as scientists learn more and more and more, there's going to be more to tell you in the future. So it's about an ongoing engagement with your genetic data. You only have to sequence once, but you can query often. It's in effect an app store for consumer genomics. Your genomic data is not going to change. The interpretation is going to get better over time. We're creating immersive, actionable, mobile genetic experiences that can tell you, with our earliest apps, at least details about your ancestry, not just where you came from, but those little stories that I was talking about before, how we've adapted, how our diet, our metabolism has adapted, for instance, as our ancestors made that shift from hunting and gathering to farming. And the era of everyone being sequenced is not, of course, limited to humans. As you heard earlier, I was a co-founder of a dog DNA testing company. We've been called the 23andMe for dogs. Embark, embarkvet.com. Lots of people adopting mixed breed dogs from shelters. They have no idea which breeds go into these dogs. They're curious about it, so we can tell you that, probably with the highest degree of accuracy that's out there. Also, about over 160 different genetic health conditions. So a lot of dog breeds have very high incidences of quite serious genetic diseases. We can tell you about that. We also have a breeder's product that allows breeders to start to weed out some of the bad genetic variation as they're choosing their breeding stock. And then, of course, ancestry. Everybody likes to think about the genealogy of their pets as well as themselves. You can go through and match up your pet with other pets in the database. So really interesting, fun company that has taken off, but co-founded by myself and Adam and Ryan Boyko in Austin back in the fall of 2015. Now, I want to wrap everything up by making this very personal. We have an individual in the room who has volunteered to talk about his genetic information. And if I could ask him to come up to the stage, if he's still here, Alan. Awesome. So Alan Muchagamba, CEO of the Angus Association, kindly allowed us to analyze his 23andMe genetic data, talk about the results. And so, Alan, you spit into a tube, probably at some point earlier this year.
I spit into a tube in September, and I want to clarify that I didn't necessarily do this voluntarily. I got told by my executive assistant, spit in the tube, so I did.
So you tested with 23andMe, and they'll tell you about your ancestry, a lot of medical stuff. I'm not going to get into the medical details here, although you have nothing to worry about. But on the ancestry side, it revealed that you are Eastern European in large parts, about 40% Eastern European, Iberian, so Spanish Peninsula, Iberian Peninsula. You've got some Southern and Eastern European mixed down there. And so you are largely of European ancestry with a real skew toward Poland or Ukraine, somewhere in Central Eastern Europe.
Correct.
Does that make sense?
Makes perfect sense. My dad is Polish. He thought he was 100% Polish, but evidently not. And then my mother's side is Spanish. So.
Yeah, and so the Spanish side shows up when we start to look at Native American ancestry, Hispanic ancestry in this case. So we saw the Iberian ancestry before, so Spanish Peninsula, but we also see some Native American ancestry in there. And so I'm guessing this would be on your mother's side.
Yeah, evidently. It's on my mother's side. It was somewhat of a surprise. My mother's side is Spanish, and a family of doctors, actually. I'm still wondering. To this day, my brothers and I are curious why she fell for a cowboy from South Texas, but that's a different discussion. But my mother was born in Texas, my grandmother in Mexico City, my great-grandmother in Madrid. So there's the native.
So we got it right. That's good. I wanted to talk very quickly about your Y chromosome. So this is about your father's 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 father. So that would be the Polish line of descent, I'm guessing. You're a member of haplogroup G, which is a really interesting haplogroup because it connects you to some famous people. When I was on Stephen Colbert's show several years ago, he turned out to be a member of haplogroup G, but probably more famous than Stephen is a guy named Ötzi the Iceman. He's a member of haplogroup G. So he is the guy who was found dating from the Mesolithic, as it's called, so around 6,000 years ago, up in the Alps between Italy and Austria, frozen in the ice. He turns out to be a member of that same haplogroup. So you're related to the famous Ötzi the Iceman.
Terrific. Did he have any genetic conditions?
Not as far as we know.
Good.
And then, of course, your Neanderthal ancestry. So it turns out that you have more Neanderthal genetic variants than around 68% of the people in the database. You're in the middle, but skewed a little bit higher, which is probably a good thing, because we now know that Neanderthals were smarter than we ever expected. They actually had bigger brains than modern humans do. They had a lot of modern human behaviors, and they had a lot of adaptations to the environment, especially pathogens, which we kind of took on board when we interbred with them. So you have a little bit of Neanderthal ancestry, which is a good thing.
That's good.
Okay, well, we're going to go ahead and end it there. If you're interested in learning more about this field, we've got a podcast called The Insight. You can get it on iTunes, wherever you get your podcasts from, Google Play. You can follow me on Twitter, and thank you very much.
Nice job.
Absolutely.